Okay, so we were discussing projective spaces. Okay, so if you recall, we have projective space, projective n space over K, which is where K is of course an algebraically closed field, and this is of course this thought of as a space of lines in n+1 dimensional affine space. All right, and we have given the Zariski topology on this. Okay, and in fact if you remember so there was a very nice picture, one giving the geometric side and the other the algebraic side. So for the algebraic side, so this is the geometric side and this is the algebraic side. So this is a picture very similar to the case to the affine case. So on the algebraic side you take the so called homogeneous coordinate ring of this projective n space, which is defined to be the ring of polynomials in n+1 variables, and it is customary to start the indexing of the variables from 0. Okay, and of course you have n+1 variables, and this is the affine coordinate ring of the projective space above, of the affine space above. Okay, so this projective space is after all affine space, the n+1 dimensional affine space punctured at the origin modulo the equivalence, which identifies all the points passing through on a line passing through the origin. Okay, all the points on a line passing through the origin in n+1 dimensional affine space are identified as a single equivalence class. Okay, and therefore in other words an equivalence class is just a line passing through the origin, and therefore this is a space of lines in affine n+1 space. Okay, and this is the homogeneous coordinate ring, which is also the affine coordinate ring of the affine space above. All right, and what you do is that of course the important structure here is that we are interested in the so called graded structure of this ring. This ring, so let me write it as S. This S is a graded ring in the sense that S is the direct sum of its degree d pieces for d greater than or equal to 0. Okay, where SD corresponds to homogeneous polynomials of degree d. S0 is of course is going to be just k, the constants which are homogeneous polynomials of degree 0, and it is this so called graded structure which is very very important. And in fact what we do is that the Zariski topology is defined like this on the projective space. You start with I in S a homogeneous ideal, namely I the condition for homogeneity is that if you take the ideal I should be the same as it should be the same as the direct sum of all its pieces intersected with SD. So you take the ideal I and intersect with SD, what you will get is all those elements in the ideal which are homogeneous of degree d, and of course if you take the sum, it will of course be a direct sum because this is already a direct sum, okay, and this will certainly be a subset of this always for any ideal. But then the condition that the ideal should be homogeneous is that this is exactly equal to this, okay, which is the same as saying that given any polynomial given any element here, each of its homogeneous components is also back in this ideal, okay, that is what it means. And you know we saw this as a geometric condition for a polynomial to vanish on a line. It is necessary, a line passing to the origin, it is necessary that the polynomial has no degrees, has no constant term, that is its constant term is 0, and every degree d piece, every homogeneous piece of the polynomial should also vanish on that line, okay, and that is exactly this homogeneity condition, okay. So once you have a homogeneous ideal, then you can define the 0 set of this ideal in the projective space, which is the set of all points here which are common zeros of all the polynomials here, okay, and of course it is the homogeneity of the polynomial which allows you to decide for sure that the polynomial vanishes at a point on the projective space. It is because it is the homogeneity of a polynomial which tells you that if it vanishes on a line passing through the origin, then it will vanish at every point on that line, okay, and so we get this, and these are the so called closed these are the closed or algebraic subsets in projective space, and this gives the projective space a Zariski topology, a topology which is called the Zariski topology. The proof that this is a topology is very similar to the affine case, okay, you can check it, and of course you have to remember that the property of an ideal, the property of homogeneity of an ideal behaves well under some product intersection and taking radicals, okay, namely a sum of homogeneous ideals is homogeneous, a product of homogeneous ideals is homogeneous, an intersection of homogeneous ideals is also homogeneous, the radical of a homogeneous ideal is also homogeneous, okay. These are all simple facts that you can check, and moreover you can also check that to check that a homogeneous ideal is prime, you can check the primeness condition only for homogeneous products, okay. So in general, if you want to check a ideal is prime, you take a product in the ideal and show that one of the factors of the product is also in the ideal, but then you can restrict this checking only to homogeneous elements if you want to check a homogeneous ideal is prime, okay. So the fact is that as in the affine case you get a very nice picture, you get you have an arrow going in this direction, and well, there is also an arrow that is going in this direction, so this is the z, this is the I, and this is give me any subset y of projective space, then I have I of y, this is the set of all, so you take the set all those homogeneous polynomials which vanish on y, and then you take the ideal generated by that. So this is the ideal, so this is, well, so this is the ideal generated by all homogeneous polynomials vanishing on y, okay. So and I also told you, if you recall in the last lecture, that yet another way of saying that an ideal is homogeneous is by saying that it is generated by homogeneous elements, okay. So since this ideal is generated by homogeneous polynomials which are of course homogeneous elements, it is obvious that this ideal is a homogeneous ideal. So you get a kind of mappings back and forth in this on this side you can have closed subsets or algebraic subsets of projective space, and on this side you can have homogeneous ideals, and you have mappings going in this direction and the reverse direction. But then if you want to make this into bijective correspondence, you will have to restrict of course well, in fact on this side I can take all subsets, okay, but and here I can take all subsets and here I can take all ideals, but of course the point is I can't take all ideals here, I have to take only homogeneous ideals, okay. But then this map always gives me something closed here, okay, because that's how Zariski topology is defined, whereas if you give me any subset, this always gives me a homogeneous ideal, okay. So if you want a bijective correspondence, what you will have to do is that just like the affine case, you will have to restrict here to you have to restrict here to radical ideals, okay, and on this side you will have to restrict to closed subsets, and then you have bijective correspondence, okay. And as before, this is as in the affine case, this is an inclusion reversing bijective correspondence between radical homogeneous ideals on this side and closed subsets here. The only thing you have to remember is that you should take homogeneous radical ideals, that is the first point. The second point is you will have to leave out one particular ideal, and that is the so called irrelevant maximal ideal. That is actually the maximal ideal that corresponds to the 0 in the affine space above, of which has been thrown out when we considered the projective space, okay. So this is a fact that I told you last time, and of course we have nice things like we have statements like so let me say that, just repeat it. Here you have closed subsets on this side, and you have a bijective correspondence on this side you take homogeneous radical ideals different from the irrelevant maximal ideal, which is usually written as S plus. It is written as S plus because it is the sum of all the, it is the direct sum of all the SDs for D positive, okay. If you take S1 plus S1 direct sum, S2 direct sum, and so on, what you will get is exactly the ideal generated by all the variables. So it is written as S plus, okay, and this is called the irrelevant maximal ideal, okay. So you have this bijective correspondence, and then of course as we have these facts like I of Z of I is rad I, and you have Ez of I of y is y bar, okay. These are all facts that we have in the affine case. We have the and of course in one direction this is trivial, the other direction is the so called projective Nullstellensatz, okay, and so you have a projective version of the Nullstellensatz, and you have these two facts, and you also have as in the projective, as in the affine case, you also have this fact that if you take prime ideals, homogeneous prime ideals, that's a subset of this because a prime ideal is always radical. So if you take the subset of homogeneous prime ideals, that under this correspondence will go to what are called as projective varieties. These will be irreducible algebraic sets in projective space. So on this side I will get projective subvariety here, and by projective subvarieties I mean closed or algebraic subsets of projective space which are irreducible. So in other words, what I am saying is just like in the affine case, a subset here is a closed subset here is irreducible if and only if its ideal is prime, okay, and so these are all things that we have just as in the affine case. And now what we do is that so we define, so we so the so what we do is that we enlarge the notion of variety to include. So far our varieties were either affine or quasi affine. So affine meant that you are looking at an irreducible closed subset of some affine space, and quasi affine means you are looking at an open subset, non-empty open subset of an irreducible closed subset of affine space. So this is X irreducible closed in some affine space, and quasi affine meant something that's an open subset of such an X that is an open subset of an affine. So you can think of it as U sitting inside X. This is non-empty open subset of X, which is an irreducible closed subset of some affine space. Okay, so this is what is meant by a quasi affine variety. So we have already dealt with these two. Now you extend the definition to include projective varieties and quasi projective varieties. So what are projective varieties are similarly irreducible closed subsets in projective space. So it is some X which is irreducible closed inside projective space, and of course you can again define quasi projective varieties, and quasi projective varieties are open subsets of projective varieties. So quasi projective, these are open subsets of projective varieties, so they will look like an open subset, open non-empty, inside X which is irreducible closed inside some projective space. So now variety means any one of the following four possibilities. So it's either it's either an irreducible closed subset or an open subset of that in affine space or in projective space. Okay. Now so we enlarge the notion of what a variety is, and then you have to note that talking about irreducibility, you have to note that projective space is also Noetherian. So I just wanted to remind you that projective space is just the quotient of the punctured affine space, and of course if you take and the punctured affine space is Noetherian, so the projective space is Noetherian. For example, how do you verify that a space is Noetherian? You show that it satisfies the DCC, the descending chain condition for closed sets. So if you give me a descending chain of closed subsets in projective space, you simply pull it up by the projection map to the punctured affine space above, and then you add the origin, okay, so that you will get a descending closed sequence of subsets in affine space. But then the affine space is Noetherian, therefore that sequence stabilizes, and therefore its image below will also stabilize. Okay, of course you will have to remove when you take the image below, you will have to remove the origin and then take the image under the projection from the punctured affine space to the projective space. So it's obvious that the projective space is going to be Noetherian. Okay, and then the moment you have a Noetherian topological space, then every closed subset has a Noetherian decomposition, namely a decomposition into a unique decomposition into irreducible, finitely many irreducible closed subsets, the decomposition being unique except for a permutation of the elements occurring in the decomposition, except provided you assume that there is no redundancy in your decomposition, namely no irreducible closed subset in the decomposition is a subset of some other irreducible closed set in that decomposition, and therefore and such sets, irreducible closed subsets, the finitely many irreducible closed subsets the union of which in a unique sense is the given closed subset of projective space, they are called the irreducible components. Okay, so this is just so you have Noetherianness of projective space, you have irreducible you have the Noetherian decomposition for any closed subset. Okay, that's because of the Noetherian property, and then you will also have this fact that topologically you know that any Noetherian space is quasi compact, therefore you will get that projective space any projective space is of course quasi compact, and in fact direct demonstration of that is that we have seen that a projective space is actually a union of n+1 affine spaces. Okay, so that's already a finite cover by affine spaces. So Pn has a union, Pn is the union of finitely many ans, n+1 ans. Okay, so but in fact any any subset of Pn being a subset of a Noetherian topological space will be Noetherian, and you know and since a Noetherian topological space is always quasi compact, any subset will be quasi compact. Okay, so well now so these are all nice things that are going on here. So in particular you must remember that if you take an open subset, if you take a quasi projective variety, then that is both irreducible and dense in its closure, which will be a projective variety. Just like if you take a quasi affine variety, it will be both irreducible and dense in its closure, which will be an affine variety. Okay, so so this is the situation. Now what I wanted to do is I have enlarged the objects in the category of varieties like this. Okay, I also want to enlarge. So I'm thinking of the category of varieties, which means I'm thinking of both. I have to think of both objects and morphisms. Okay, the objects of course I have enlarged because I have added projective and quasi projective varieties, but then I have to enlarge the definition of morphism, and you know the definition of morphism, the affine or quasi affine case is that it's a continuous map that pulls back regular functions to regular functions. Therefore if I want to enlarge if I want to define morphisms which involve even projective or quasi projective varieties, I have to tell you what are meant by regular functions for projective or quasi projective varieties. Okay, and the answer is very simple. Just like the affine case where a regular function is just a quotient of polynomials locally, in the projective case you only require that it's a quotient of homogeneous polynomials of the same degree, and you put the same homogeneous degree so that you get a valid function. Okay, so so let me say that so you know, so suppose you are having a subset S in projective space. Okay, and you take F and G in in S super H. This is the union of all the SDs, d greater than t greater than or equal to 0. Okay, let me all right, so let me take d greater than or equal to 1. Okay, let me not take non-zero constants. Okay, so you take two, so I am taking two homogeneous polynomials. Of course you know I cannot evaluate a polynomial on, even if it is homogeneous, I cannot evaluate a polynomial at a point of projective space. The homogeneity of the polynomial will only tell me that it is what I can uniquely always say is whether the polynomial will vanish at that point of projective space or not, but I can't give, but if it doesn't vanish it can't give you a particular value. Okay, that's because if I plug in a point from projective space here, then you know there is a common multiple which is floating around, because the points in projective space are common ratios, that's why they are called homogeneous coordinates, and that whatever constant multiple can always be pulled out of the evaluation, and it will come out with a power which is equal to the degree of the homogeneity of the polynomial. So but the point is that if degree of the homogeneous degree of f is equal to the homogeneous degree of G, then you know okay, so maybe there is no harm in including 0 also, because anyway constant functions will make sense. So if so if both of them have the same degree, then you know f by g makes sense as a function into k in S intersection the complement of Z of g. Okay, so the point is that if I plug in the problem is that if I plug in a point of projective space into a homogeneous polynomial, then if I change the representation of the point, then a scalar will come out, and it will come out with a power which is equal to degree of the polynomial. But if I take such quotients, then these powers will cancel. Okay, therefore you get a well defined function. So all this is telling you is that you know homogeneous polynomials are not enough to define functions, but quotients of homogeneous polynomials of the same degree certainly define functions on appropriate subsets of projective space. Of course appropriate subsets I should by that I mean the denominator polynomial should not vanish, okay, for me to be able to evaluate f by g at a point. Okay, so now this is the prototype of what a regular function is for a subset of projective space. So so we make this definition that so here is a definition, a function h from x to k where x is a quasi projective or projective variety is defined is said to be regular at x in x if it locally looks like a quotient of two homogeneous polynomials and the number of variables is equal to one more than the dimension of the projective space in which x sits. Okay, so if x belongs to z of g, where x is a subset of Pn and h restricted to ux is equal to f by g restricted to ux, where ux is an open neighborhood of x contained in z oops x should not be in zg. In fact I want to divide by g and I want to evaluate it at x, so g should not vanish at x, so this has to be corrected. X should not be in the 0 set of g and this neighborhood should be contained in the complement of this 0 set of g, the complement of. So this is the definition of what a function, a regular function at a point means. Of course here f and g are in the homogeneous coordinate ring of the projective space, okay, which is well polynomials in the right number of variables. So this is going to be k of x naught. Okay, so the idea is very simple, and of course you know it's regular at a point automatically means regular in a neighborhood of a point. Okay, so because you are requiring this not only at that point, you are requiring it in a neighborhood of the point. So the definition of regular function as in the affine case already says that it is regular at a point if and only if it is already regular in a neighborhood of that point. Okay. So now what we do is again define the ring of regular functions on the projective variety or quasi projective variety. We define Ox as before, and it becomes K algebra. Okay. So regular functions, Ox is of course the set of all global regular functions, namely functions which are regular on the whole of X, which are that means functions are regular which are regular at every point. Okay. And if you take the set of all such functions, that is a K algebra, because sum of regular functions is regular, product of regular functions is regular, and when you multiply a constant with a regular function, that is again regular, because a constant is also thought of as a constant regular function. Okay. So so we have this ring of regular functions on your quasi projective or projective variety, and the point I want to make is that as before, every regular function is always continuous. Okay. Regular functions elements of Ox are always continuous, and that is again something as continuous of course for the Zariski topology. So elements of Ox are going to give I have still not defined morphisms, so let me come to that later. Regular functions of Ox are always continuous. Okay. And the continuity is obvious because of it's obvious if you look at if you remember the fact that the Zariski topology on the projective space is a quotient topology of the topology above. Okay. So if you give me a regular function on a subset here, okay, then if you compose it with the projection, okay, you will get a regular function on the affine space, okay, above on a subset of the suitable subset of the affine space above, and that is continuous, and that will tell you that the inverse image of closed sets are closed because of the definition of the quotient topology, and therefore what will happen is that regular functions are it is very trivial to see regular functions are continuous. Okay. Now that we have defined this, what we can do next is now this paves the way to be able to define morphisms. So now how do we define morphisms between two varieties? Is just this definition is the same as before. It's a morphism between two varieties is just a continuous map that pulls back regular functions to regular functions. Okay. So definition remains the same. Only thing is now you have your objects are more. You are not only considering affine or quasi affine varieties, you are also considering projective or quasi projective varieties. So you can think of a morphism from an affine or a quasi affine or a projective or a quasi projective variety into another variety, which is again one of these four types. Okay. So the definition of a morphism is the same as before. The definition of a morphism is the same as before, and again what will happen is that we again get the following important theorem: if X is any variety and Y an affine variety, then we have a natural bijection from the set of all morphisms of varieties from X to Y to the set of all homomorphisms of K algebras from AY to OX. We saw this theorem where we were thinking of X only as an affine or quasi affine variety, but then the same theorem will the proof will go through. Now if you go back and look at this proof, you will see that the same proof will work even if X is a projective or a quasi projective variety. Okay, so this theorem still holds, the theorem still holds. And if you remember, I think I call this map as alpha, and what was this map? Well, if you give me a morphism from X to Y, then it goes to alpha f, which is just the pullback of regular functions. It is a map from AY to OX, which will pull back a regular function phi to you give me a regular function on phi on Y, then if you compose it with f, you will get a regular function on f on X. So first apply f, then apply phi. Okay, this is just the pullback. This is just the pullback of regular functions, and you must remember that AY is the same as OY. AY and OY are the same because Y is an affine variety. Okay, so the affine coordinate ring is the same as the global regular functions. Okay, and so this is the map we defined, and then you also have the inverse map which goes in this direction. And what is the inverse map? If you start with phi yeah, K algebra homomorphism from AY to OX, then what you do is that you recall that Y is an affine variety, so Y sits inside some A n. So it means the affine coordinate ring of Y is just the affine coordinate ring of A n modulo the ideal of Y. This is how you define the affine coordinate ring of a affine variety, and then and this is, well, this is going to be identified with k x1 etc. Up to x, or let me put k y1 or maybe t1 etc. up to tn modulo iy, and and so you have the ti bars here, which are regular functions. They are just the coordinate functions on the affine space in which Y sits. Okay, and you are just a ti bar means just it can also be thought of just as ti restricted to Y. Okay, because after all, taking this quotient amounts to restricting polynomial functions to closed subset Y. Okay, so now each ti bar will go to a certain regular function in X and use this bunch of n regular functions in X to define a morphism from X to affine space, and show that morphism actually that map is actually a morphism which factors through Y and for which the alpha is phi. So so the diagram is that from Y what you do is you get a map into an, and this is given by so here is G, and G of Y is just phi of t1 bar of Y dot phi of tn bar of Y. It is this n tuple. So and the fact is that this factors through so I'd rather call this map as G, this as G tilde if you want, and it factors through X. Oops, this should have been X. Sorry. So this should have been X. So these all should have been small x's. So this map is from X to an, and it factors through Y and through a morphism like this, and phi is actually phi, so let me write that below. Alpha, the alpha of this G is actually phi, okay. So this is the inverse map, this is alpha inverse, this is how we got this bijective correspondence. You can check that the whole proof goes through if you allow X also to be a quasi projective or a projective variety, there is no difference, okay. The proof does not I mean really the proof really did not depend on the fact that X was affine or quasi affine, okay. So you can check this theorem. So in particular, you know, if I take y equal to a1, it will tell you that the morphisms from X to a1 are the same as the regular functions on X, okay. So just as in the affine case, the regular functions are the same as morphisms into a1, there is no difference, okay, there is really no difference. So the same proof works, and the point I want to make is here is a very important theorem which I would like to say in this connection. See, we saw that if you put y to be a1, you will get regular functions, okay. But more importantly, we saw that, you know, if you take any affine variety which is different from a point, okay, the fact that it is different from a point means that its ideal is different from a maximal ideal, and therefore when you take its affine coordinate ring, it will have lots of polynomial functions, okay. So it is going to be polynomial ring modulo some ideal which is a prime ideal but it is not a maximal ideal, okay. This is a finitely generated K algebra which is an integral domain, and this has lots of polynomial functions. So if you give me a affine variety which is different from a point, there are a lot of global regular functions which are given by a lot of polynomials, okay, whereas this is not the case for a projective variety, okay. So the theorem is that if X is a projective variety, then O of X is isomorphic to K. O of X is just K, okay. So maybe I will let me put isomorphic, okay, where by isomorphism I mean so what I mean by this is that every global regular function is the function that corresponds to a constant, it is a constant function, and there are only global regular functions are constant. So you must think of this as an analog of the fact that, you know, if you have a compact complex manifold, then the only global holomorphic functions on that will be constant, and that is just because of Liouville's theorem, okay, that a bounded entire function is a constant. So it somehow you must think of X as being compact, and therefore it does not admit any global functions which are not constant, okay. But the proof of this will require some more definition, so I will defer that, okay. But what you must understand is that if your variety is a projective variety, then it has no global regular functions, which are no non-constant global regular functions. Of course constant functions are always there, but if you want non-constant regular functions, there are none, okay. This makes life a little bad in the following sense, because, you know, we have seen that if you have two affine varieties, then they are isomorphic if and only if their affine coordinate rings are isomorphic, and you know, for an affine variety the affine coordinate ring is the same as the ring of regular functions, okay. So an affine variety can be kept track of by looking at its affine coordinate ring, and the affine coordinate ring does not change no matter in which projective space you are embedding the affine variety as a closed subset of, okay. But this is not going to happen, so let me repeat that. If you take an affine variety, if you take its affine coordinate ring, that is the same as its ring of regular functions, that ring is independent of the embedding of this affine variety as a closed irreducible closed subset of some affine space. If you change the affine space and you embed the same affine variety into some other affine space as an irreducible closed subset, then if you compute the affine coordinate ring there, you will still get an isomorphic ring. Okay, so you can keep track of an affine variety by looking at its ring of functions. That is what it says. The ring of functions completely controls and keeps track of the affine variety, but this is not true for projective variety, because for a projective variety you take two different projective varieties, they unfortunately the ring of regular functions is just k, it is just the constants. So there is no way to it becomes hard for you to distinguish between two projective varieties. Okay, then of course so this leads to other problems, and in fact this is what leads you to study so in fact this should tell you, you should expect that if you take a projective variety and try to define the coordinate ring of a projective variety, which is analogous to what you would do for an affine variety, namely take the homogeneous coordinate ring of the ambient projective space. If you have a projective variety embedded in an ambient projective space, what you do is you take the homogeneous coordinate ring of the ambient projective space and go modulo the ideal of this projective variety, and the result is again a graded ring, because you are taking a graded ring, okay, and you are going modulo an ideal which is a homogeneous ideal, it is a homogeneous prime ideal. So you again get a graded ring which is an integral domain, which is a finitely generated K algebra, but the problem is that if you change this embedding, you take the same projective variety and put it into some other projective space and calculate again look at the coordinate ring, the homogeneous coordinate ring, it will change, it could change, and it will. So it is very so the way in which a projective variety is embedded in projective space has a it does not have a uniformity about it, okay, and this tells you that it gives you the following fact, I mean this it gives you the following philosophy which is the basis of all higher study about projective space. It is the fact that if you want to study all the functions, if you want to study the geometry of a projective space, you want to study geometry of a projective variety, you must look at its embeddings in various projective spaces, that should reveal its geometry. Okay, the way its homogeneous coordinate ring changes as you embed it in various projective spaces, okay, that should give you some grasp about the geometry of the projective variety. So it is but nevertheless this does not mean that there are not that you do not have properties of projective variety which are intrinsic to it as a variety. Okay, so what it tells you is that you can no longer work with global regular functions on it, because there are not any non-constant global regular functions. Okay, so I will come to the proof of this later, but then I want to tell you only one thing. If you look up put these two together as a corollary, you will get the only morphisms from a projective variety to an affine variety are the constants, are the constant maps. So this is something that you can see immediately, because in this bijection, suppose X is a projective variety. If X is a projective variety, then OX will become K, okay, and therefore I will get morphisms from X to Y in bijection with homomorphisms of K algebras from AY to K, okay, but every K algebra homomorphism from AY to K is surjective, because it is a K algebra homomorphism, the image has to contain K. So every K algebra homomorphism from AY to K will be surjective, which means its kernel will be a maximal ideal, and therefore then the set of morphisms from X to Y, okay, will be the same, will be in one-to-one correspondence with the maximal ideals of AY, but the maximal ideals of AY correspond to points of Y, and therefore what will happen is that what this will translate to, if you look at it, it will be that the the only morphism from a projective variety to an affine variety will be the constant map that ends whose image is a single point. And how many points, how many such morphisms will you have? As many morphisms as there are points in the target variety, okay, and each point in the target variety, which is an affine variety, corresponds to a maximal ideal of Ay, mod which you get a homomorphism from Ay to K. That is what this bijection says. So as a corollary, what you get is that the only morphisms from a projective variety to an affine variety are the constant maps, okay. There are no non-constant morphisms, there are no morphisms except constant maps, okay. And of course this also should tell you another corollary that you can get is that if a variety is both affine and projective then it is a point, okay. This is also something that you can easily realize, because you know if the variety is projective then its global regular functions are just constants, and if it is an affine variety then you know the ring of regular functions is will now be just the constants, and for what affine varieties will the ring of regular functions be constants? Only singletons which consists of points. So if you put the condition affine and projective on a variety then you are reducing it to a point, okay. So these are two easy corollaries of this theorem and these two theorems, okay. So I will stop here and continue in the next lecture.